The theme really is about building bridges. Another theme that we're going to see in this talk is how we need to acknowledge diversity. So within the field of neuroscience and AI and in the world, there are a lot of different views that might not always seem compatible, whilst in reality they are. Often they're kind of constrained by the language we use or the preconceptions of how other people think about what they say. And it's funny that it's how pervasive that is within religion, but also in the sciences. Even though we try to seem objective, as if that's a real reality, in the end, we're all kind of trying to push our own agenda and opinions, which is, in my opinion, why neuroscience is kind of still fractured and not as coherent as I want it to be. So on to the talk. I am not an AI scientist. I'm not a data engineer, any of that sort. But I do believe that we're in a very important time of the world in our history. Because we're trying to build artificial intelligence without knowing what actually intelligence is. And it's quite a strange thing, because it's one of the most human aspects of our experience, what intelligence is. And I think a lot of you people see themselves as very intelligent, but what that actually is it's quite contentious, controversial. We can't rely on philosophers, we can't rely on scientists apparently. So it's time to kind of try to bind all the different efforts together. And at the moment, two of the biggest efforts are from neuroscience and AI. It's no coincidence that two of the biggest people in AI right now, Geoffrey Hinton, for example, or Demis Hassabis from DeepMind, have an extensive background in both cognitive sciences and computer science. And it's this synthesis of two different fields that makes it so powerful. And I hope to put forward this theme to you guys as well. Maybe some of you are in AI research, and hopefully I can encourage you to take more inspiration from neuroscience, despite it might seem inaccessible sometimes. All right. So yeah, that's the full disclaimer. I'm no expert on anything AI or engineering specific. If anything needs clarification, I'm not sure about everyone's background, please feel free to interrupt or ask something, unless there are really any questions, and we'll leave that for the end. The main goal here is simply to foster discussion, to try to build bridges between people that might benefit from each other in this time where we're both basically all in our infancy, both in AI and neuroscience, on intelligence. If you want very in-depth reading, a lot of these topics come forth in this very good paper by Lake and other researchers who are in this intersection of brain and machines. It's published last year, and it's a very comprehensive review of what I would describe as an algorithmic approach to intelligence, which I'll diverge on later. So again, it's about continuing the tradition. So AI, artificial intelligence, and human intelligence have all the same questions, the same concept, the same challenges, just use kind of different language and approach. And there's a mutual benefit to try to bring these together, even though it might seem quite difficult. And it's a very long-term mission. I need to emphasize, intelligence is not going to be solved in the next few years, decade, anything of that sort. But it is very important, not just for science and technology, but also for education and for human well-being in general. The rigidity of the way they talk about it is basically what I think is preventing the crosstalk. And it might lead to a bit of a challenge, some challenging of conventions in my talk, but I do think that it's for the better in the long run. So I hope I can help you join me in this mission of integration. So we're just going to first go through a very broad overview, kind of looking back at a very human, historical approach to intelligence in our history. And I'll give you a crash course, a bit of a biased view of what I think the brain is and what makes it interesting, again, at a more conceptual level, and try to show you how there are so many different types of levels and domains of analysis when it comes to that we'll have to translate to intelligence. And hopefully then I can show you how we can build then towards a common language for intelligence. So some of you might know the movie Ex Machina, about the AI, or there's this term Ex Machina. Ex Machina was actually a phrase from the ancient Greek theater, where they had this big story or a big play, and it was really convoluted, and how are they going to solve this? And basically just take God for the machine, just fix everything with one thing. It's nice and easy, just ties everything together. And that's kind of similar with religion. I know it's a strange approach, but religion is almost universally prevalent in any major civilization. And it was very appealing to them because there were so many unexplained things in the world. And they get this, boom, this big, coherent, self-reinforcing, consistent system to explain what's happening. And it resolves a lot of uncertainty, and it's quite nice, because even though we might not understand everything, even though there might have been genius out there, they were just unable to reduce that uncertainty. They were knowledgeable about what was unclear, but not able to bind it together. That creates a certain frustration. So that power of adoption, that universal aspect, I think that's something very telling. Something very telling that I'll reframe in a more rigid framework. And another parallel here is that religion has been very connotational. It's been very, the flip side of this ease of joining everything together is that if you really want to understand it, you've got to disambiguate it. And that's something we need to do for intelligence as well, because let's be honest, who actually knows what intelligence is? It's a social construct for a lot of different things we don't really understand. It's comfortable to say intelligence without knowing what it is. So one of my favorite books is by Igor Alexander, Professor Emeritus from Imperial, one of the earlier engineers who got interested in AI and even artificial consciousness. And I love the word, the name, the world in my mind, and my mind in the world, because it emphasizes this relation between the world and the mind. Basically what the brain does, in a very basic way, is extract information from the world. That's basically where AI is right now, just pattern recognition. But that's really the easy part. The hard part is knowing how to put these things together in a sensible way to accommodate whatever function the brain actually has, to accommodate adaptive behavior. So arguably, we've evolved beyond sense. Obviously, we're doing a lot of things that are not really for survival. So the key thing about the brain is no longer survival. It is adaptation, which allowed us to survive. So in this disambiguation, we need to first look at how much of it is related to the social context and how much is actually intrinsic to how the brain works. So we're going to talk mostly about the latter part, about this intrinsic idea of intelligence, and we can touch upon the contextual aspect of intelligence later. For example, the shared knowledge we have in society is a big source of our intelligence. If you put a genius baby 2,000 years earlier, he probably wouldn't turn out very well. He just didn't have the information to take in and make good use of it. Vice versa, if you take someone from 2,000 years ago and put it now in the modern age, you probably turn out to be a decent human being, capable of doing intelligent stuff. So going again to the brain, it's a very big thing, the brain. It's very complex. And talking about it is often complicated because people have this biased preference to one way to looking at the brain. So in acknowledgement of that problem, I want to distinguish 3 levels of analysis, something that was popularized by the neuroscientist David Marr a few decades ago. So the brain is a self-organizing complex system, and it requires distinctive levels of analysis to really understand and function. You can look at the most basic level of analysis where it's just little features, little elements, little neurons, but you've got the emergent higher level behavior that is at least as complex that we aren't really close to modeling, to be very honest. So the 3 distinctions is, at the most basic, implementation, algorithmic, and computational. You can draw several analogies there to substrate, activity, and function, hardware, software, and purpose. And every level acts as a certain constraint. If you choose one kind of implementation method, then you probably constrain your ways you can derive algorithms, and vice versa, and same for algorithm and purpose/computational. And acknowledging these distinctions is very key to prevent miscommunication. I often read things in AI research that seem to misconceptualize things in neuroscience because they assume it pertains to either all of these levels or just one, and that prevents them to really take the value that the other has for their own research. Now, the reason why I'm focusing on this distinction is because I think herein lies a certain key thing if you want to create a common language for intelligence. And this is very crude, I know, but basically it's these 3 levels, right? The human is the red, the bloody part, and the artificial is the blue, sterile part. And you can't really do much about the implementation, right? We're stuck with silica. Whether you use memristors and transistors, it doesn't matter. You're going to create artificial neural networks. And if you want noise, you've got to design a kind of noise. Whereas with the brain, everything's already there. All that noise, all that variability, all the different kinds of neurons, they're just there. Whereas for the purpose, the computational, with AI, it depends on the designer, and with human, it's basically the adaptation to the environment. But the more interesting part is in between. In between, there's this abstraction that as deeper you go in that abstraction, the more independent you become of the implementation and the computational. Basically, what I'm saying is there's this overlap where you possibly could use the very same language and perspective for algorithmic, independent on whether you look at the machines or to humans. And if you're ever going to look at neuroscience research, I think that is the kind of perspective you want to find inspiration. So just for a quick discussion, who here actually has an idea on what the brain actually optimizes? Anyone want to take a gander, take a guess? Yes?
Short-term memory to long-term memory gets compressed.
All right, I like that. Okay, anyone else?
Energy consumption.
I really like that as well. I'll come back to that later. Yes?
Information retrieval.
Information retrieval, all right. That's very nice because I get three-partite distinction, right? We've got the implementation level, this very basic biological energy consumption. Then we have the interface between the mind and the world, which is information retrieval. How do we do that? The interface is basically our senses. And then we've got something more algorithmic, but the actual architecture, infrastructure of the brain, which is short-term memory to long-term memory. So that's really beautiful. And it shows that we have different biases to what level we kind of want to go to for analysis. Anyone want to take a gander at the objective of the brain? Yes? Controlling the body. All right? Having fun. All right? Yes, in the back?
Emotions.
So emotions and? All right, we're going to come back to that later as well at the end. So this is very beautiful. Again, we see all these different kinds of perspective, which is all kind of correct in a way. And that, again, shows the difficulty and the challenge in trying to understand the brain. We'll leave that bonus for later. So let's go back all the way to the foundation that has nothing to do with either, but pertains to both. So what is actually information? If you ever read things like the brain doesn't compute, just ignore it. I know I'm biased, but ignore it. That's absolute nonsense. We have information. It doesn't work without information here. So we have information in the brain, and information is a tricky concept, but I think the most elegant and truthful concept is a difference that makes a difference. Because if it doesn't make a difference, then it's not real. It doesn't have any causal relevance. It's basically just noise. Well, even noise makes a difference. So again, that fundamental definition I prefer. But what is the value of information? Why is it so central to the brain? There's one theory called the free energy principle, which I'll shortly go by later. It basically formalizes the idea that in the brain, the physical value, like energy consumption, is equivalent to the informational value. And that is something very elegant, and that's intertwinement of the substrate and the informational abstraction is something that might also be of relevance for AI. But information is, again, very broad. If you go beyond the fundamental, you quickly diverge in the ways you can look at it. In the brain, you can look at simply representation. What actually does it create? How does it go together? Models, representations, schemas, templates, all the same thing. And more importantly, how do they change and adapt? How do you determine whether you change one model to model A or model B? And how do you message? How do these models actually interact together? How do they inform each other on how to actually change and how to actually do? How does it all come together again to control your body and do behavior? That's all very complicated things. Again, we're not really close to solving either AI or neuroscience. And this disambiguation of information needs to be addressed in parallel to intelligence. So AI and neuroscience, in a formal sense, still are very much focused at the implementation. Almost all the big breakthroughs in AI, it's all about the technical implementation. How do we really make these neurons work and do stuff? At the very basic level, and far away to the point of actual behavior, control, emotion. That's all large-scale stuff we don't even know very clearly in neuroscience. And sooner or later, this algorithmic level needs to be addressed because you can imagine if you just build a lot of narrow AI, you can't just merge them together and get this very general AI. It doesn't work like that. So at some point, we need to have an algorithmic discussion, and I hope that this is one that facilitates that. One key aspect there is the representation, model building, the abstraction of what comes in. And arguably, I think that is what allows multi-sensory integration, what is key to this transferability, the generalization, possibly later what allows narrow AI to come together. So let's go a bit more concrete to the brain. So this is an image I really like. This is an image of synapses and neurons in the prefrontal cortex. And in a child still developing within gestation to newborn, all the way 6 years. And you see the peak is at 2 years. In 2 years, there's the most synapses. After that, it just goes downhill. Downhill when it comes to connections. But obviously, it doesn't go downhill when it comes to knowledge. The prefrontal cortex is for execution, control, planning. It's kind of the conductor of the rest of the brain. But somehow, it gets less connection. And you think, wow, that's kind of weird, right? Because you want to account for all the complexity we get in life. So I think these kinds of things are counterintuitive. At least it's counterintuitive to me when I first heard about it. But it's very illuminating to how we should approach AI. Again, that's very relevant to the energy consumption comments, by the way. This is one of my other favorite images. So what you see here is analyses of tons of fMRI data. If you don't know, that's like neuroimaging, where you scan a brain. And here they looked at the connectivity, the effective connectivity. How much does one part of the brain talk to or influence another part? Now, in this kind of analysis, you've got to choose a seed. What is your actual focus on? What is your primary frame of reference? And here they've done it for every sensory modality. The gustatory is like taste, interoceptive is the internal state of the body, auditory, hearing, and so forth. Why this is so interesting is because you need to realize that these are the inputs to our brain. 6 modalities. And everything else comes from that. Everything we construct, everything we guide our behavior with comes from the information from these 6 modalities. Now, the darkest part is basically the input, the most surface level. And the lighter it is, the more deeper it goes into abstraction. And you see there's a very diffuseness to it. And this all comes together again into actual concrete abstract behavior. And that's something we need to figure out with AI. One way that I like to frame this is basically as naturally emerging operating systems or an internal interface. We can reflect on what we actually think about. We can strategize. It is not an isolated endeavor. The fact that you're conscious of your actions, that you're conscious of your thoughts, shows that this information comes together in a coherent process. All the relations you are aware of, these are real relations in your brain. That means that all the information in your brain is contextualized with all the other information in your brain. And that is something that is not really approached. We've got some approaches to modeling your own memory, some approach to self-supervised learning, but this is the peak we need to go for. And to do this, we need something called compositionality and systematicity in that representation. You can't just have the data that fits the outside. We need to know how it works, know how we can use it to control our body. And this relates to a concept called complexity, which is specifically both very differentiated and both very integrated. So having parts that are very cleanly integrated together, but also very distinct from other parts, which is very key to the brain. One of the hottest approaches to neuroscientific analysis is complexity measures. When it comes to the actual compositionality, that's actually quite relevant to Geoffrey Hinton's latest work on capsule networks, of having this level of complexity within a very small element or component of your representations. And this abstraction is what allows generalization. You abstract above the concrete, which makes it more relevant or informative of other parts related to that. But how did we get there as humans? How did we actually learn all this, infer all this in a way that creates consistency and coherence? One way to look at it is unifying principles. In the last 5 or 10 years, we've gone really hardcore on these unifying principles, and more specifically predictive coding, which is originally actually a computer science method. So basically the idea is that the brain constantly is generating expectations or predictions that we compare with the incoming inputs. So anything that ascends into the brain is just error signals. Errors on what the distinction is between expected and actually seen. What comes down, top down from within to outside, is simply expectations, which are grounded in these models we've talked about. So the formatting is a bit off, but one specific formulation that is very mathematical is called active inference by Carl Friston here at UCL. And that unifies action, perception, inference. Action and perception are the interface with the world, and inference is basically what's in between, what makes that loop kind of close. And you see that in his formulation of what is actually being optimized, you can distinguish multiple components. The first light blue one is an epistemic component, just about the information of what it actually is. Second, you have this intrinsic value of your actual body, of your internal state, like homeostasis. And you have an intrinsic and extrinsic value, your modeled beliefs on what you prefer to do and to achieve. These kind of approaches are very powerful and at the moment very popular in neuroscience and might be also of relevance for AI.
Sorry, what was the name of the researcher?
This is Carl Friston. He's at UCL in the Functional Imaging Lab. It's also where Demis Hassabis did a postdoc or PhD, I forgot which one. This is a very overly simple model I found on the internet. It's not that I fully agree with it, but I think it's very telling. So here, it's just the IA bits. It's just a model between the sensors and actuators, but that's understatement. In fact, the model should model all of that around it as well, because if not, it's just a mechanistic component. It's actually in controller of how this model is aligned with everything around it, which is why it's so crucial that it models not only itself, but also the context in which it's situated. Going back to how we learn and infer is something called curiosity. It's funny because it's key to human endeavor. We're curious people. That's how we get intelligence. But artificial curiosity has been untenable for a very long time. As far as I know, the most interesting research has only been in the last few years or something. So actually, my master's thesis was on artificial curiosity. I won't go in detail, but basically the game here was to just pick one of the three colors. It's either red, green, or blue. And you see like these three colors, which are just the situation. It's very abstract, but it's doable. And the key here is to find the abstract rule that corresponds to the situation. The situation's rule is determined by this color, so it's one of three rules. And obviously, that's a very large combinatoric space. You can imagine every kind of rule you want to solve this, which is shown by the fact that I've got like a quarter of the university students unable to do this task with 360 trials. They got really mad at me. Some people, they did it in 10 trials. I think the key here is that what they're inferring is nothing really about the world right there. It is purely abstract. Their motivation to solve this because they can do this task with a relatively high amount of scores, but it's not really efficient. It's convoluted. Their model is a combination of a lot of competing hypotheses, and it's very effortful to do this task with all that competition going on. So they're intrinsically motivated to reduce their model complexity and do this task with a simpler solution. And yeah, so I think that's very key to people. We try to infer the hidden patterns, the hidden rules of our worlds, again, which is why religion was so powerful. If anyone's, yeah?
Please explain the task.
Sorry, I don't think we have the time, because I think Christian's going to get mad. So if anyone's interested in the more specifics, this is a formalization of this. And the only thing they're really inferring is the rule right up there. If you're into probabilistic methods, everything else is very clear. Nothing here is ambiguous whatsoever. The only ambiguity is finding out the mapping between the colors, which are the stimuli, and the correct or the optimal choice. It's the only thing that's unknown. Yeah. So went through a bit fast, so maybe just a break. Who wants to take a guess or have a suggestion about what do you think the conscious experience tells us about our mind? Anyone daring to take that question? If not, we'll go on. That's fine. All right. So coming back to basically the key point of this talk is the tradition of mutual inspiration. So it's actually started off with, in 1986, parallel distributed processing by McClelland and Rosenblatt. And before that, also the perceptron. And that is kind of key to how we should see things. There is a lot of convergence between AI and neuroscience, and the power of which we kind of distill piece by piece. And we can't rely on these coincidences, and we can't rely on scientists who happen to have both these academic backgrounds. In the time, there's been a tension between symbolic and sub-symbolic approaches to AI. Basically, pattern recognition versus model building. We still see this kind of distinction. But, why not both? Probably because it wasn't practical at the time. But if you look at the brain, it's most likely both. If you look at the most basic, there's no symbols. That's unfeasible. That's not very logical. But if you look above, you need some kind of approximation to symbols to make it work. And again, one way to see capsule networks is as a complex symbol. One of the biggest annoyances of me in psychology is the black chapter of behaviorism, the idea that we're nothing but behavior boxes. Very annoying, very silly that it took so long. And I feel like it's kind of similar with AI now. It's all performance. You train a neural network based on its actual performance, the reward, and that's how you train the internal models. And then you get these neural networks that do a game very efficiently, very well, great performance. But if you actually kind of think what they're doing, they're not doing it very human, and they're extremely inefficient. If you actually look at the data they get to do similar human performance, it is disproportionately huge. And I think that's the consequence of us forsaking this importance of what's actually happening inside, not in a way of blaming, but simply because it wasn't clear yet. Again, urging for this clarity on the algorithmic level. So how do humans do it? In the paper that I first mentioned, there's been some suggested core ingredients to intelligence. First one they call developmental startup software, basically the boot-up system. Basically, the implication is that when we're born with certain innate dispositions for certain domains of intelligence, domains of competence. Things like intuitive theories on numbers, on space, on physics and causality, and even psychology, a theory of mind. These things are innate. No matter what child's bar varying unfortunate disorders, they all have a very natural way to learn this. And to have an AI that also has this by nature is key. And most likely, this is not due to the neurons, but due to the architecture, again, the algorithmic design. Second to that, we have this rapid model building. We don't need a lot of data to learn things. Kids are notoriously smart. We need to have AI that is like kids, that are behaviorally stupid, kind of useless, but they learn really fast. Adults can't do that. We don't learn words that fast. We don't learn concepts that fast. We don't generalize that fast, but kids do. And we need to figure out how to make that as well. When it comes to representations, we need this very rich compositional and systematicity in our models. Again, that's reflected in how we have this conscious awareness of our internal experience, awareness of how our actual contents relate together. Because without that, we can't possibly be as efficient. Me talking here, I have a conception of this room and I know how to behave without a lot of efforts. And I think that tells a lot about the amount of work we still need to do. And I think one key theme here is learning and inference. We have a lot of learning models or learning algorithms, but that is all, again, on the implementation level. Even though it's called learning algorithms, it's algorithms on a neural level. And we need to figure out a certain bigger picture when it comes to learning and inference. In addition to that, I think what it all comes down to, in my opinion, is, again, an emphasis for algorithmic, getting some kind of insight there. And what I find nice about Kraken is it's basically on that algorithmic level. It is very flexible. It is, by nature, by design, focuses on inference. And I think, if I understand correctly, there's a very huge compatibility with integration of conventional neural networks. So the value of that could be that, imagine you have this whole range of neural networks, and some of them just happen to show the behavior you want, and you infer that it's because of the way they created some kind of representation, some kind of self-models, some kind of architecture, and you want to look into that. And you want to somehow distill that and transfer it to other neural networks as some kind of a top-down effect, as some kind of constraint. I don't know if it's feasible technically, again, not an engineer, but I think this kind of approach would be very interesting to somehow optimize our advancements and research in the algorithmic level of description. On top of that, I think the beautiful thing about graph-like approach is very humanly interpretable. This graph-like approach is basically what the brain does. We create these virtual nodes that we connect together in not just in semantic maps, also conceptual maps. How much time do I have left? A couple of minutes, okay. So in addition, we've talked a lot about models and representations, right? But they're very fuzzy. There's no grandmother cell. There's no one cell that says this is Jennifer Aniston. There might be one very strongly correlated to Jennifer Aniston, but there is no cell that is fully encompassing that concept. Basically, all the representations are very distributed, so we can make flexible representation of things. We can recreate representation based on these compositions, on these components. This is why you can imagine three-headed dogs. This is why imagination has been so powerful in the past. But the difference between that actually imagined representation and the actual basis is the static versus dynamic. How do you determine how you put these things together? Like we said in the beginning, how do you put these things together? Like Heikel said, it's short-term memory versus long-term memory. And the short-term memory is basically the act of trying to figure out how to put these things together. And when you make a sensible composition or reconstruction, you basically put it in the long-term memory. But this basically shows that we have this very difficult problem. You can only have very few things dynamically instantiated, connected together. And how do you do that? How do you choose which parts actually get to merge together in this dynamic instantiation? That is a very difficult problem in neuroscience, and key to consciousness has led to a research on metastability, of having a metastable representation, basically on this having an oscillation of activity that creates a coherent network. Yeah, and I don't know if anyone knows it. If you do know, please come to me afterwards, but I don't know if AI is actually doing that, because I think that is very much key to learning and inference. Yeah, another common language of interest I think is interesting is something just universal about networks. The way networks are structured tells us a lot about the functionality. The complexity measures I talked about before are, for example, very interesting in consciousness research, trying to figure out what degree of consciousness we actually have, or it actually has a certain relation with intelligence as well. The complexity, again, in a very specific sense, the way it's differentiated and also integrated. If it's just differentiated, you just have a lot of parts you don't know how to put together. If it's just integrated, you have this enormous rigidity, and there's no creativity. So I think I'll leave it for now. I apologize if it wasn't as in-depth, but there was a certain time constraint. I was hoping to give you a certain conceptual broadness over technical depth, and I hope you enjoyed this. And thank you for your attention.